All right, chapter 2, we talk about the atmosphere as a whole. Basically, we're just given a very quick overview of how it's composed, its structure, some theories of how it was originally came about. So, with that, what is the composition and structure of the atmosphere? Well, the atmosphere covers the whole world. So, for example, if you have a dust storm in Africa, that dust is going to move from Africa, across the Pacific, across the Atlantic Ocean, into parts of the Caribbean and the United States. And this is just a really neat picture of that, how how the whole world, what they do at any one part impacts another. And atmospheric weather can go from beautiful to really bad very quickly as you're learning, looking at your memorable weather events. So we think of the atmosphere as part of the Earth system. A system is just a group of components that interact together to cause whatever scientific thing we're trying to explain. And in this case, when we look at the Earth system, we want to understand things like the biology of it, or the geography of it, or the hydrology of it, which is the water. And the atmosphere is all part of that. It's just one piece. The atmosphere actually is really thin, and its mass, over half of its mass, can be found within 18,000 feet. So if you're climbing in the Rockies and going to the top of the Rocky Mountains out there, almost half of the atmosphere is below you. And if you get to 32 kilometers up, or 20 miles, 99% of it. So think about it. If you were driving in a horizontal, it doesn't take that long if you're doing 60 miles an hour to drive 20 miles. Well, guess what? It doesn't take that long to go through our atmosphere either, upwards. So it's a very thin layer. It has a heck of an impact on our lives, but it's a very thin layer. So the atmosphere is composed of oxygen and nitrogen, which nitrogen is the main component, and a whole bunch of other gases such as water vapor, carbon dioxide, argon. There's all different kind of other gases that make it up. But the primary two are nitrogen and oxygen. Notice they have a percentage applied to them. Well, the atmosphere at the Earth has so many molecules in it. Higher up you got, there's less of those molecules, less parts to it. So even though the amount of oxygen stays the same, the percentage-wise, the number of oxygen molecules is significantly less. That's why as you climb up a mountain, it gets harder and harder to breathe. I had a lot of training for a number of years in Boulder, Colorado. Boulder, Colorado sits at 6,000 feet up. Well, every time I flew into Denver, and I lived on the East Coast at the time, I was at sea level. So I was used to plenty of oxygen, sea level. Every time you went to Denver and you started taking walks, all of a sudden, a little harder. It took your body a week or so to adapt to having that less oxygen to deal with. And when we used to go up into the Rocky Mountains from there, Rocky Mountain National Park is only not quite an hour away from Boulder. We used to go up to 13,000 feet sometimes in the mountains there, and it was a lot tougher to breathe. That's because of how few oxygen molecules are left. Even though the percentage is the same, there just aren't that many of them. There are other aspects to the atmosphere. We have aerosols. Carbon dioxide is obviously required for life, photosynthesis. Water vapor. We want to make sure we get plenty of water to live. And there are man-made pollution. That's all part of the deal. So we study the atmosphere by using what we call the scientific method. Scientific method is all about we observe, we want to see what's going on, and then we want to know why. So I'll give you an example that I dealt with. A lot of thunderstorms develop to the west of Virginia and move across the Appalachian Mountains. And sometimes as they move across, they weaken, and sometimes they actually strengthen. Well, we can come up with theories as to why, but we asked that question. So we worked with some scientists at North Carolina State University, and we formed some hypotheses, some theories about why this happened. So then we started looking back at past cases to say, okay, do these theories hold? Well, some of them did, but we looked back and tried again. We found some that actually did, so we were able to develop and look for certain things that said, oh, if this is in the atmosphere and if the atmosphere works this way, looks this observation, these thunderstorms that are coming from West Virginia or out to the west are going to keep moving and come right on through in Virginia. And we got much significantly improved accuracy. So it's how you use the scientific method to understand these things. Of course, we want to look at the atmosphere and understand it overall. We have simulations of tornadoes out at Purdue, numerical models. Everything I want to talk about in this course could be applied to numerical models. None of the models can be solved. I'll tell you flat out, no mathematician on earth today can solve the equations that exist for weather. However, we can approximate it, and that is what we do for these numerical models. In order to understand what's going on, you need to have a lot of observations. One thing that has developed over the last 20 years is ASOS. It's also called AWOS, depending on where you are. ASOS is at the main airports. AWOS is at secondary airports, smaller airports. But the more of these surface observation systems, and they're all automated, there's no people there, they take a scan of the whole atmosphere at the surface from a surface perspective. What you see plotted on your surface plots that I've been having you look at. Another part of this is the cooperative network, which just has precipitation, max and min temperatures, and COCORAS, which is a bunch of volunteers that measure precipitations, hail, lightning, thunder, all kind of severe weather possibilities. Radiosondes or dropsondes. Radiosondes go up. They're carried up by a balloon. There are little instruments that's attached to that balloon. By doing that, what you're getting is observations in the vertical. Dropsondes are just the same kind of instrument, just dropped from above by an aircraft. We look at remote sensing. We can't always be where we want to be to see what weather. Weather, when you think about it, covers every square inch of the earth, and we just don't have observations at every square inch. Radar is one method of remote sensing. We send a microwave signal out. It bounces off particles such as raindrops or dirt, even bugs, and we can process that and determine where precipitation is, what the motions are, the clouds or the air. Satellites are another method. And this is the atmosphere as a whole. We've chosen to define the atmosphere by temperature changes. In other words, the troposphere, where we live. Temperature drops in the troposphere on the whole. If you averaged out the temperatures in the troposphere, they would be falling continually. Stratosphere, on the other hand, they're warming. Then the mesosphere, they're dropping off again. In the thermosphere, they're warming up again. So those are the main sections of the atmosphere. And when you're between them or at the edge of them, there's always a pause. So in other words, if you're up above the top of the troposphere, you're going to get a tropopause. The ionosphere, where the auroras occur, we've had a lot of them this last fall. Some down as far south into Virginia's, West Virginia, Ohio, all the way down. Very spectacular. I got some neat pictures from some friends of them. And they have formed depending on the amount of activity of the sun. The stronger the sun's activity is, the further south these are going to spread. So all right. Let's go with one more thing I wanted to show you. And that will be an upper air sounding. I talked to you about the radiosondes and the dropsondes. doing these soundings? Well, here they are. This place is Detroit today. All we're doing here, on the left-hand side is pressure dropping. There's 1,000 millibars, 900 millibars, 800, 700, and so on. Then straight vertical lines up are temperatures. So we plot an actual atmospheric temperature and a dew point, which is just a measure of moisture. So if you look down at 900 millibars, here's 900 millibars, you see the temperature there, if you went straight down, was about -10. Dew point, well, it's exactly at the same spot. So if the dew point and the temperature are together, it means there's clouds. So in this section, right here, it's cloudy. And the temperature is dropping, as you can see, with time over height. So part of the troposphere. Now, you'll notice right here, it doesn't. It actually warms slightly, and then it begins to drop again. This happens at the top of fronts. There are various fronts in the atmosphere. We've talked about warm air rising above the cold air along a cold front or warm front. Well, these are literally the top of the fronts, right here and right here. They're in a cold air mass. There's like one cold front that's through here, another one, they're sitting up here. And we also talked about the tropopause. Well, the tropopause, think about it, temperatures warm or tend to begin to warm with height when they get into the stratosphere. Could be an argument made right here in this area is a tropopause because the temperatures are pretty steady. But they do fall off again up here, so I'm not 100% confident of that. But colder air, tropopause is going to be lower. Warmer air, yes, definitely going to be up in the 100 millibar range up in here. Finally, the last thing plotted on this is winds. And you can see here they're pretty much west winds. So all this cold air is moving from the west to the east. I just wanted to give you this a little bit, help you hopefully with some of the chapter 2 and some of the vertical profile of the atmosphere you're going to be seeing more and more of. Now, let me know if you have any questions.